This is Learning Assessment Problem 10.8. The problem-solving strategy here is that of magnetically coupled circuits. We are shown a network here which contains two mutually coupled inductors, and the question is to determine the amount of energy stored in these inductors at a time of 10 milliseconds. We are told that the frequency in the system is 60 Hertz. The expression for the energy stored in a pair of mutually coupled inductors at a particular instant in time is given by the expression. First, there is a term due to the current I1 flowing through the inductor L1 as a function of time. Then there's a term due to the current I2 flowing through inductor L2 as a function of time. And finally, there is a term due to the mutual coupling between the two inductors, and this contains the product of the two currents, I1 times I2. Notice that there is a plus or minus sign associated with that expression. If the currents in both inductors flow into either the dotted terminals or the undotted terminals, then the sign is positive. Whereas if one of the currents flows into a dotted terminal and the other flows into an undotted terminal, we will choose the minus sign for that mutual coupling energy term. So now we'll proceed to use Kirchhoff's voltage law and solve for the phasor currents I1 and I2. First, around the loop I1, we'll have 2 plus J2 times the phasor current I1. That's the impedance contained in the I1 loop. And then plus J1, which is the mutual coupling term, times the phasor I2 current. And that's equal to that voltage source in the loop I1, 12 at an angle of 30 degrees volts. Similarly, we can do KVL summation around the loop I2 current, and we'll have 2 plus J2 minus J2 times the current I2 plus the mutual coupling term J1 times the current I1, and that sums to 0. Now we'll write these two equations in a matrix format. So here we have the impedance matrix times the current column matrix is equal to the voltage matrix. Now we'll use Kramer's method to solve for the two phasor currents I1 and I2. The determinant delta of the impedance matrix is equal to 2 times the quantity 2 plus J2 plus 1, which is equal to 5 plus J4, and in polar form that is equal to 6.403 at an angle of 38.66 degrees. Now we'll proceed with the solution for the I1 phasor current, which will be equal to the ratio of the determinants, which is equal to 24 at an angle of 30 degrees divided by the delta determinant expression, 6.403 at an angle of 38.66 degrees. And this result is 3.748 at an angle of minus 8.66 degrees amperes for the current I1. Similarly, we'll solve for the current I2 by the expression, and evaluating this ratio of these determinants, we will have that I2 is equal to 1.874 at an angle of minus 98.66 degrees amperes. So we now have the two phasor forms, or the frequency domain forms, of the currents I1 and I2. Now we'll have to convert these into the time domain in order to solve for the energy storage. We are told that the frequency is 60 Hertz, which gives us a radiant frequency of 377 radians per second. So I1 of t will be the transform of that phasor I1 expression. That will equal 3.748 times the cosine of 377t for the omega t part of the cosine function, and then minus that phase shift angle for the I1 phasor of 8.66 degrees. Now, depending on what sort of calculation instrument you use, you'll probably need to convert this angle in degrees to radians. So the 8.66 degrees is equal to 0.151 radians. Now we can begin to evaluate the current at the particular time of interest, that is t equals 10 milliseconds. At t equals 10 milliseconds, cosine of 377 radians per second times 0.01 seconds minus that phase shift 0.151 radians is equal to minus 0.888 for the cosine part of the time function. Then we can say that I1 at 10 milliseconds is equal to the amplitude 3.748 amperes times this minus 0.888 for the cosine, and that is equal to minus 3.329 amperes. So we'll need that number in order to calculate the energy storage in the inductors and the mutual inductance. Now we can look at the I2 of t time function, and this will be equal to 1.874 cosine of 377t minus 98.66 degrees. The 98.66 degrees corresponds to 1.722 radians. So the current I2 at t equals 10 milliseconds is equal to 1.874 for the amplitude cosine 377 radians per second times 0.01 seconds minus 1.722 radians for the phase shift, or I2 at 10 milliseconds is equal to 1.874 times the cosine portion, which is minus 0.459, and this is equal to minus 0.861 amperes. Now we'll need to know the inductance values and the mutual inductance value. We have the expression for the reactance of an inductor is equal to omega times the inductance, and this gives us L is equal to X sub L divided by omega. So the L1 value will be 2 ohms divided by omega, which is equal to 2 ohms divided by 377 radians per second, which is equal to 5.305 millihenries. And that will be the same value for the inductor L2 because they both are given as having the same impedance value. The mutual coupling value M is equal to 1 ohm divided by the 377 radians per second, and that is equal to 2.653 millihenries. Now we can proceed to write down the expression for the energy stored at 10 milliseconds in this inductor system, and this will equal 1/2 times the inductor L1 times the square of the current I1 flowing through that inductor. Then we'll have the energy stored in inductor L2 and finally we'll have again the positive addition of the mutual inductance energy. And when we do the math, we have that the energy stored in this inductor system at 10 milliseconds is equal to 3.896 times 10 to the minus 2 joules, which which is equal to 39 millijoules.